Reservations in two-way slabs by means of yield lines. This video deals with cases 16 to 20, and this is about concrete slabs who are on three sides fixed and on one side freely supported. This is about case 18, dealing with an edge square hole. We have a rectangular concrete slab with a square hole in it on the top of the slab. The position is D4 and then the size is D1. It's a one-way slab, so it means B is between A and 2A. Square reservation, D1 is equal to D2. And the vertical position, D1, but smaller than D4. And it's at the edge, so it means that D3 is 0. Then it should be between the yield lines. And that means that for D4, you have the left limit and the right limit. For the yield lines, for the negative bending moments, there's a yield line here, but this is cut where the reservation is. We have a yield line on the right and a yield line on the bottom. Then we use the 30, 45, 60 rule. This is 60 degrees. This is 30 degrees. The yield line starts where the axis of rotations are crossing. It's the same for here. And then we have 45 degrees because this is the same as that. And then we connect the two. And these are now the yield line pattern. We can write the limits by filling in the values of S1 and so on. And to visualize the range here, then you see a square hole ranging between the left yield line and then move till it touches the right yield line. So this reservation is not cutting any yield line unless the yield line here where the slab is fixed. We will now calculate the work done by the internal forces, which is for the orange rectangular elements. It is this side, which is B minus S1 minus S3 times A, but we have the reservation in it, so we have to deduct this reservation. And we know that this reservation has a limit left and has a limit right. That's why we introduce this limit. Otherwise, we cannot use one particular formula or closed formula. And we subtract the reservation, which is, of course, V1 times D1. And then the maximum deflection is on this point compared with the delta here. So this delta is D1 over S4, which is here. And the mean deflection of rectangles is the half of it. So that's the formula. And for the green part, it's of course A times S1 and A times S3, the mean deflection delta over 2. We can fill in the different variables and we arrive at this equation. The work done by the internal forces is then the yield line around this axis here, which is B minus D1 divided by the angle of rotation, delta divided by S4. So B minus D1 divided by S4. This line, yield line projected on this axis gives you B divided by S4. Then we got this line, which is A divided by S3. And this yield line is also A divided by S3. On the bottom, we have B divided by S2. And here also B divided by S2. And here we have A divided by S1. Then we arrive at this expression. D is equal to E. We get M from it. And this is the formula for the maximum bending moment. The first thing we notice is that this formula is independent of D4. So notwithstanding that we have put limits on D4, this formula, there's no D4 in it. It means that we must be very careful that we always check that the conditions of D4 are fulfilled before using this formula. We give you now an example of a square slab with a reservation in it. The slab of 200 millimeters, concrete cover 40 millimeters, floor finish 2 kilonewton per square meter, and a mobile load is 20 kilonewton per square meter. And we want to find what is the needed reinforcement. First, we look at the yield lines of the negative bending moments, and then we use the 30, 60, 90 rule. This is 45 degrees, this is 45 degrees. Here too, this is 60 degrees, 30 degrees, 30 degrees, 60, and we draw the yield lines. The maximum load in ultimate limit state is 1.35 permanent load plus 1.5 mobile load gives you 39.45 kilonewton per square meter. We identify now the different variables. Alpha is 1 and alpha 1 is d1 over a, which is 0.38. The maximum bending moment is then given by this formula, and we find that the maximum bending moment is 21 kilonewton meter per meter. We calculate the mean lever arm of the reinforcement, and it gives us 152 millimeters. The needed reinforcement is 1.1 times the maximum bending moment divided by the lever arm and the yield strength of the reinforcement. It gives you 390 square millimeters per meter. That means 8 diameters, 8 per meter, and you have 402 square millimeter per meter. You can also, instead of taking diameter 8, you can fill in diameter 10. You will have slightly different lever arm, and it will be 150. And then you can recalculate the reinforcement, which is slightly more, and then you have diameter 10, 5 per meter. So this looks a nice reinforcement. Second example, we have an existing slab and they want to make a reservation in it, 2 meters from the edge, and the reservation 2 by 2. Is this possible? You do not have the necessary information. You don't know what size of reinforcement is or what the actual load was on this slab. So we suppose that the reinforcement top and bottom are equal and that slab was calculated correctly in the beginning. So we know the parameter alpha b over a is 2, and because 10 divided by 5, and a1 is 2 divided by 5, so it's 0.4. And we can calculate now the maximum bending moment without the hole, but we don't know the load where to calculate it for, so we say m0 divided by the load equals to a value that is only dependent on geometric characteristics, 0.925. And then the maximum bending moment with the hole, we can calculate this, and it's 0.887. So this means that the bearing capacity by making a reservation like that is 104%. So you can make a reservation of 2 by 2 meters without losing bearing capacity of the slab. This is, of course, because this portion of the yield line is cut, but it's a small portion if you compare it with all the other yield lines. So because you do not cross those yield lines, you end up with not touching the bearing capacity by making the reservation. Bearing capacity is defined as 100 times the maximum bending moment without the hole divided by the maximum bending moment with the hole, or you can say it's 100 times the maximum load with the hole divided by the maximum load without the hole. In formulas, it's like that. We use non-dimension parameters. And for this case 18, we know that this condition must be fulfilled. And we are now looking at D4. Remember, D4 is not coming, it's not implicit in the formula, but how do we cope with this condition? So the bearing capacity can now be calculated with the formulas of the previous slides, and you have this formulation. On the x-axis now, it's alpha 1, which is the size of the reservation. We know that this size must be between 0 and 0.5a, so alpha is half. And on the y-axis is the bearing capacity. And we do that for different values of alpha. This is for a square slab, this is for a rectangular slab. So these are the two limits. It's the green, the blue, and the black curve. We can see, for instance, for the blue curve, when alpha is 0.25, then the bearing capacity here is 100%. 800. So you are not touching the bearing capacity. For alpha equals 1.5, alpha 1 here is, for instance, 0.3. Then we look at this limit and we can fill in alpha and alpha 1. And you see alpha 4 is between those two values. So that's possible. There's no problem at all. This condition is like the left-hand side is this, and the right-hand side is this condition. So it's a hole which is going from there to there. But now let's look into that a little bit closer. This is the limit of alpha 4. How do we deal with that? Well, at alpha equal 2, that is the black curve. If alpha is 2, then you can calculate alpha 1, which is 0.776. But 0.776 is out of our scope because alpha 1 must be smaller than 0.5. So this upper condition for alpha equals 2 does not bother us. Then we take alpha equals 1.5. We fill in alpha 1.5 and we find that alpha 1 is limited to 0.58. That's not a problem because it is limited to 0.5 for our formulas. So this condition does not play a role. But then when we arrive at alpha is equal 1, which is the square slab, then alpha 1 is 0.388. So this means the red curve is for alpha equals 1. This means that for the value of alpha 1 bigger than 3.9, that this curve is not valid anymore because you do not fulfill the conditions for alpha 4. So it means that the red line, it's the bearing capacity as alpha 1 equals to 0.388, which is the limit. That's this one. For the blue curve, well, alpha is 1.5. You have also here somewhere outside the graph, this value, you will also have the intersection. So this does not play a role. But here, this piece of values are not valid. Then we see on the left-hand side that this is almost 100%. So that's an interesting area because when it's more than 100%, that's fine for us. We don't bother. But when it's smaller, then you can have a problem. So let's look at this area. So this is the graph of the previous slide. This region we will enlarge, make it bigger. Again, this is alpha 1 from 0 to 0.3 to this point. And the bearing capacity from 98 to 102. So it's this portion of the graph. You see, these are the three curves ranging alpha from 1 to 2. And the region below is the one which is interesting for us. So you can see roughly that if you make a reservation of this case 18, then there is no bearing loss at all in the region where the alpha 1 or the size of the reservation is 1/4, larger than 1/4 of the smallest size of the slab. So that means this region here. This is 100% here. So this region here. When we when we have a hole which is smaller than 1/4 of the smallest size, then the loss that you will have is maximum 1%. So we don't bother about that. But it's just the principle. You can with this type of method, you can calculate what is the minimum or maximum size of the reservation that I can make. When alpha 1 smaller than alpha 100, that's the definition of alpha 100, the bearing capacity will be smaller than 100%. So this is the alpha 100%, which is a function of alpha, of course. This is the alpha 1, 100%, alpha 1, the size of the hole. And then you see below this curve, it's smaller than 100%. We must avoid that. And above, it's more than 100%. So now you have two regions that are separated from each other, and it's easy to see what the maximum and minimum size of your reservation will be or can be. The bearing capacity, by definition, of slab alpha, which is B over A, and the size of the reservation is alpha 100. Well, the bearing capacity of all those points is 100. That's the red curve. That's the meaning of the red curve. You can easily calculate this. What is alpha 100? And then this red curve is this formulation. Then you will see, for instance, for alpha 1.5, you could make a reservation which is at least 0.25 times the smallest dimension of the slab. If you do not do that, then you end up here in the lower side, and then you will end up with losing some bearing capacity. Not much, but some. And then you can easily see it. If you take this point at 1.5, then you will see 0.22 of alpha 1, you end up here, and otherwise you end up there, which is bigger than 100%, and this is smaller than 100%. But the difference is very small. As a conclusion, a square hole at the edge of a rectangular concrete slab type 18 has no significant loss of bearing capacity as long as the yield lines are not crossed. So you have a visualization of it. It's a square hole like this with different sizes, but when you do not cross or cut the yield lines, then it is fine. It is okay.